Okay, so I think the next part we were supposed to do is just the clean channel, but I've just combined those with tone controls because really there's not a whole lot to talk about by themselves on the clean channel. You know, there's a compressor, buffer, and a tone control. So we'll just talk about these two things in different videos. Now here's a tone control. This is just mine. I wouldn't worry about this for now. So this is how I have it written out, and we're going to use this Duncan's tone stack actually. I mean, it's awesome. So I'm going to open up a couple instances of this program. Now there's tone stacks. Everybody talks about them, use them. There's a lot of information out there, so I'm only going to talk about maybe some things that I think nobody else seems to talk about, or there's maybe some misinformation about. First thing is, well, the first thing you'll notice is like this bass control is a log, okay, and I don't stock a lot of log pots. I mean, there's nothing wrong with it. I mean, they're great, but I just tend to build stuff with the inexpensive things I have on hand. And so I want to show you a little bit of a trick for using a log pot versus a linear pot. And it's not perfect, but it's sort of, it works well enough. So the first thing you'll notice, well, this is kind of an easy swap to do. When you look at these circuits, you have 220K treble potentiometer, and it's going into this load, which is 517K. And that's why you have a bass drop there, basically. I mean, let's just kind of make a smiley face here with both of these, just to sort of demonstrate things. I tend to look at it this way. So, you know, you can't really get any more. You get this loss here, right? There's nothing wrong with that. It sounds good, actually, with the guitar rolling off a little bit of the bass like that. This is kind of a signature Marshall tone stack sound. So, and it, you know, kind of tapers nice too. So what you can do to kind of get something that's similar-ish, if that's a word, is what you'll do is if you're using this kind of thing in a circuit, instead of going into 517K, you want to go into something, you know, much larger. Now, I don't use 220K because, you know, you can scale these up or down, right? You can if you take every capacitor in this whole circuit and you divide it by 10, and you take every resistor in this whole circuit and you multiply by 10, the curve looks identical. They call that scaling. You don't have to do it by 10. You could do it by 2 or by 0.3 or whatever. But you divide your capacitors. I'm sorry, you would multiply the resistors and divide the capacitors by this factor, and you get the same thing. We don't need to demonstrate that, but oh, you give me a second, we'll do that. Okay, I just did this. What I did was, you could see I took in this case I wanted to reduce all these resistors down, so I divided every single resistor in here, even the source impedance and the load, by a factor of 10. Then I took the capacitors and I multiplied by 10. See, from 22 nanofarads up to 220, etc. So this is scaled. Now look at the graph. It looks identical, right? It is, because that's just how the math works. So saying that, I don't tend to work with as big as pots as this all the time. I'm usually like in the 50K to 20 to 50K range, something like that. So I'm just kind of showing you that. Now I'm going to get rid of this one here, and we're just going to. Do you want to save it? No. So okay, so here's two original Marshall tone stacks. I haven't changed anything about them. and I want to say, well, I want to use a linear pot on the base rather than a log. Here's the trick you do, okay? The next stage you go into, you make much higher than the tone stack. So I'm just, for the illustrative purposes, I'm going to make this 10 megs, right? We can see that bass loss goes away for the most part. And then you take the bass pot and you put the resistance down to equal whatever the treble pot is. In this case, it's 220K. Now, this won't be exact, okay? But it kind of puts it in a usable range. You can see this is, now, you know, this might be, there might be better value like 150K or something like that. This is kind of an odd value anyways. But you can reduce it by like to where it's almost matching like the treble, maybe a little bit less. But anyway, so when you've got this cranked up all the way, and let's, this needs changed to linear, okay? So now we can kind of compare these two. They're not the same, but it's kind of close enough. And you're probably not gonna, you can actually change other things about the circuit to get it to work for you. But okay, this is with it all the way turned up. You can see it's got a little more bass. We'll go like maybe halfway down. Go halfway down on this. You can see the bass doesn't quite trail off as much. You can pull it down all the way. You know, a little bit different curve, but you can kind of, you know, work other values in to get it to get a little bit better match. Kind of see this is going up to about 50%. This is probably around 30-40%. So the taper's not exactly the same, but in a pinch or even in your design, you can kind of use something like this. So I'm gonna here. Let me just pull this out for a minute, and I'm gonna just throw my tone stack up there. There it is. I'm gonna put it into here, and I'll be back in a second. Okay, so let me point this out. You know, this is a clean channel going through the compressor, goes through a buffer. So here's the point. There's a buffer there. I guess it's got 1K, so it's got an output impedance of around 1K. So let's see how that compares to this. See, so this source impedance should be about 1K, which I don't really have to have that there. I could make it a little less, but this is what's in the circuit. So, okay, so here's a comparison of the two. Now, I'm not trying to clone the Marshall stack here, but it just kind of gives you an idea of what's going on. So, and so you can see my bass response is up a little bit more. The treble is just down like half a decibel, something like that. Move it down to the halfway mark. Move this to the halfway mark. You can see it's a little more responsive from 5 to 10 than mine. Let's see there. Go from 5 down to 0. Down to 0. It's kind of a similar response, you know. So let's push this up. Okay, you can see that looks very similar, I think. Pull down the treble, very, very similar. Now, where this differs, I think my mid-cut is more prominent. You can see it. To get my mid-cut to be about the same, you've got to go up to about 2, and I think that's a little closer to what would be comparable. So mine dips down a little bit more. You know, I could go up on this. A little bit up on the mid controller or something like that. But what's nice about this this tone stack is actually real simple values. 1 nanofarad, I mean, these are orders of 10K, 1 nanofarad, 100, 100. These are 50, 50, and 5. So just real common linear values, and it behaves, you know, I don't know, similar. Sounds fine too. I mean, this isn't like that big of a deal. I think that dip here, I should have a little bit higher resistance there, but I think I used, you know, if you put like a 10K, it might work better. Yeah. Well, I don't know. Let's see here. Anyways, I don't know. I just put it back to 5K. I fooled around with this and just got it sounding decent with these basic values. But you can see the treble and bass are sort of the same value, and this is a lot greater than this. So that's, you know, that's kind of basically how I built the tone stack. I just used this here. So now, what else to say about this? Something that comes up somewhat is like when you put this in a stage, you know, like you're going from this stage to this stage, and anytime you have stages like this, you gotta really know the input impedance and the output impedance. That way, you'll know. You'll make sure that the impedance matching is correct. Whenever you go from one stage to the next, you're supposed to go up in order of magnitude, basically. So, you know, if you have an output of 10K impedance, like this output of 1, so you should at least go up to an input impedance of 10K. And then whatever the output impedance of this, you're supposed to go up another notch. Now, let's kind of just look at this. Let me see here. Say what, we'll do it this way. To find out the input impedance of this, the reason I'm showing you this, again, this is talking about something that I don't see talked about, and that's why I'm talking about it, and that is the input impedance and the output impedance of a tone stack. Now, what you're going to find out here is there isn't really one input and output impedance. It depends on whatever frequency you're looking at, and also where the controls are placed. So let's first just take a look at this simulation in action. Might as well get rid of this one. Oops. Okay, let's try this. Just kind of running this. I just have a volt. This is a Bode plot. Okay. Tell you what, I'm gonna play. It says AC of 0.7. We're gonna make that 1, because I think 1 is 0 decibels. Okay. Yeah, it's in microdecibels. So. Okay, so what do we have here? I'm going to get rid of this tracing, and I'm going to get rid of the phases. Okay, and this is the bass going up and down, the mid going up and down, treble going up and down. You can see it's, you know, this is what I have. I've got a simulation of the bass and mid and treble all being varied. And I'm just going from their lowest value to their highest value. I'm not like doing a bunch of stuff in between. Nothing wrong with that. I just, it's just kind of, I'm just looking at the extremes, right? So these are the extreme settings of the tone stack. And that's what it looked like in the Duncan's tone stack here. That's kind of what you're seeing, only I think they even have something like that where you can hit sweep and look at different things. But actually, I don't know that it actually gets all extremes, because, you know, it doesn't. I think that might be a little bit of a bug. But anyhow, so here's what we're talking about. Now, we're going to look at the impedance, but when we look at it, usually you look at a stage and you'll say, what is the impedance at 1K? Well, that doesn't really work here because we need to know the impedance across the complete spectrum. And let me get out of here. And the way you do that, this is kind of a trick. I don't know if you call it a trick, but it's some method for finding the input impedance. So here's what you do is, if you kind of look at this as a black box and you think, well, we're sending a signal through there, and you say, well, there's a voltage here and then there's a current going across along this path. And so you take V, V versus I, and that ends up being the impedance that it's seeing. And so let's just do that. Okay, so here's the voltage, here's the current, and we're gonna just take this and divide by the current, I at V1. Okay, now that I divided this to, this should be like the input impedance it's saying, so I'm just going to get rid of this. Okay, I'm going to get rid of the phase stuff because we don't need to look at that now. Zoom to fit. Now, this is in decibels, which is not what we want. We'll look at linear. Okay, so here we go. This is a... this is starting at like 32 all the way up to 16K, and these are the input impedances that this source is seeing. You can see in the treble, I'm hovering over this, it says 8.5K. If you look like down here in this area, when I hover over it, it'll tell you it's 8K. Or is 13K. So the output impedance, the input impedance, in the high area is around 8 to 12 kiloohms. Around 1K, it looks like 10 kiloohms, 14 kiloohms. Okay, so we're talking about like in order of like, I don't know, around 10K. Then you go down here in the base, you're like, whoa, that's a lot different. So you've got a 23K all the way up to 39K. So it's sort of the base, I think the base is seeing, some of this in the treble. Let me see here. Tell you what, I don't want to do this wrong, so we're going to vary them one at a time real quick. So if you look at this, we're going to go from the lowest point we can, which is 8K, go to the highest point is 40K. So what that means is if you plan on this stage being represented by, you would want to assume the lowest. If you want to be careful, you'd say, well, we're going to pick the lowest, which would be 8K, as being the input impedance of this circuit that we're going into. Because if we assume it's 8K and we go 10 times lower than that, then we're okay, because this won't matter. It's way up above that. Because again, you always want the next stage to be 10 higher. So if you start at, say, I said 800 ohms, and then times 10 would be 8 kiloohms. Then you're it's going to be 8 kiloohms or above, and you're kind of fine, assuming that. So the point is, you can see there's a variety of input impedances that this source is seeing. Like in this case, it's varying from down to 8K, and there's this variation right here. If this here going up and down, this is basically due to the mid control going up and down, and this is due to the base control going up and down. So you sort of have to, if you're really designing carefully, you should sort of think in maybe bands like, lower and then mid and highs in terms of impedance matching, because you have to sort of match those different bands. Or you can just, again, use the lowest value and just say that this stage is represented by that lowest value. But then when you use the output impedance, now you need to use the higher value. And that'll sort of avoid as much signal loss as possible. It's not always actually necessary. Sometimes you can use this to your advantage if you need some roll-off or something, some bass roll-off, and plan for that. But at any rate, there's another way to maybe look at this, and I think this is useful. It's not directly related to our to the preamp I'm working on, but it's easier to look at if you think of this in terms of a just a mid cut. And let me draw this up and I'll show you that. Okay, I just copied this. What we're going to do is we're going to turn this into just a bridge T filter, and that way you can maybe look at it a little bit easier. So okay, so we're just kind of removing the treble control here. It's a 50K pot, so we're just gonna leave it up all the way. I'll zoom on this while I'm doing it here, make it easier to see. So we're just gonna replace this with 50K resistor. There we go, 50K. Again, we're converting the tone stack to a bridge T filter. Okay, next thing we're going to do is, if we make this bass just arbitrarily large, since it's turned up all the way, and just get rid of it. Okay. Likewise, we're going to turn the mid all the way down because we're making a cut, so we just take this out too. Now you could, if you wanted, leave a resistor there, variable resistor, turn it up and down to turn this mid control on and off. I guess I could do that. Let's just call this mid. Can't hurt. I mean, it's sort of like oops, that's not what I wanted to do. Okay, bear with me here. Do one of these jobs. That's kind of weird. So, all right. Next, what we're going to say is that let's see, this so the next thing you look at is there's we're sort of trying to turn this into a bridge T filter. Now this is 1 nanofarad, and anything that does go down this way is gonna see 100 nanofarads after this resistor. So this is like 100 times, letting through 100 times more high frequency than the 1 nanofarad. So this basically is kind of like a wire almost. It just lets signal through here. So you can just kind of do this, and let's see what this looks like here. Oh. Let's see here. Just a minute. Oh, I see what I did. This thing has to be in curly brackets. Yep. Alrighty. Let's see there. Okay, you can see it looks like a mid control going up or down. here's the, let's get rid of these phases. You can see it looks just pretty similar to the mid-cut. And that's kind of a way to go from the tone stack to just a Bursty filter. Let me sort of redraw this just to convince you that a little bit. Let's see, there should be. That should look just like a Bursty filter, just like that. Now, if you're not really that savvy with, and you know, these aren't exactly the same, but they're awfully close. If you're not that savvy with you know, using LT Spice or Spice simulations, you can kind of, if you ever need a mid filter, you can do it like this. Let's say you want the Marshall, yeah, let's just use Fender, why not? You want the Fender mid-cut, all right? Do this. You make this arbitrarily large. I'm just going to make it 500 mega ohms. I mean, that's silly, but it's the same thing as just removing it from the circuit. You can make this one like 1000 microfarad. So that's just arbitrary. That's just basically a wire going across there. And you can leave this down, or you can just change it to 0 if you want. Let's put 1. But so this is sort of, you just remove this, stick a wire there, remove this, and you're left with the Bursty filter, and this is what it looks like there. Let me see, and you can also put just a huge load on it to see if that's causing any effect. And this is basically if you're going from like a low impedance source, and then you're going through a Bursty filter, then you go to this you know, higher load, and this is what you're looking at here. So it's just a way of using it in this, I guess it's not really intended way, but it's kind of works. So let's look at the, I'm just going to change this to, okay. So let's look at this tone control and see, well, what does this look like as far as the input impedance. Okay. So I'm doing that same calculation. V override, change it to linear, get rid of these phases, zoom to fit. Okay, now, what are you noticing here? Oh, this is the mid control, yeah. Since we have a mid control in there, you're seeing what's going on there. Okay, so there's about 8K, 13K. This is the higher input impedance. And that's with the mid control going up or down. Let's just take this out for a minute. And we'll just kind of look at it this way. Okay. Okay, remove that. Remove these. This. All right, so basically you're left with like 8K in the treble area and like 50K in the bass area. If if you look down here, 8K is about 10K, and 50K is about 50K. So this is sort of where you're getting that base impedance, and this is where you're getting that treble impedance or high frequency impedance. So that kind of gives you an idea of your maximum input and output impedances in the frequency spectrum. Like, this is where I think those numbers are coming from. So you want to kind of look at this one as kind of controlling that high frequency input impedance, in this is sort of controlling that. This treble pot is kind of controlling the base input impedance. And I know that may be confusing. It's hard for me to make it any easier, but the point is you gotta think in terms of the frequency spectrum when you're going through a tone stack, and think it through, like how do you want it to behave as it goes through the tone stack. If you just pick this number and you say I got to be 10 times less than that, and you just pick this number and say, well, I've got to be 10 times greater than that during output, then you're kind of fine using those rules of 10 in terms of Thevenin's theorem, I guess it's called. But sometimes you can get by, like, if this is controlling the base, so to speak, and this applies to the base, sort of the base area of the frequency spectrum. So if you're going to a stage here and you don't mind a little bass rolling off, in fact you may even plan for it depending on what you're doing, you can actually kind of use a little bit lower number for impedance matching, and you'll get that bass impedance mismatch, but you won't get it at the treble area. So it takes some thinking, but you know, this, again, I think maybe people don't talk about the input impedance of a tone stack very much, because you've got 3 different bands and they all can be set in different areas. So I tend to think in terms of like the minimum and maximum, and these are kind of your 2 numbers to look at for that. Boy, I don't know if there's anything else to say about this tone stack stuff. I mean, I think to summarize it, I would say the tricks that I've learned are that you can sort of make the bass and treble equal, and then go into a next stage that's much higher than your tone stack, and that'll give you a response that's kind of similar-ish to a log pot. I mean, I think that's a trick. And then I think just looking at the whole circuit as a whole and trying to figure out, well, what is the input impedance, output impedance of the thing, as you can kind of look at the treble pot and this resistor, and that'll give you kind of a range of how you should estimate the impedance of that stage of your circuit. See, I think that's enough on tone stacks. Hopefully you learned something from that. If you didn't, I mean, you can always skip it or just rate it badly or something. I don't know. And if anybody else has anything to add about these tone stacks, you know, let me know. I always thought it'd be neat to do a video on the big muff, because it's really easy to understand, way easier than this tone stack. I may do that if I get a little extra time. There's really simple explanations for that. But, all right, you take care. Thanks for watching.